Everyone, myself Tejaswami, and today I am going to presenting my IC number 1 of aircraft structures, and the topic is a thin wall channel section subjected to combined bending MX and MY, transverse shear force SY, uh, top flange, bottom flange, where is two materials are given, which is aluminum and steel. So here is the given data. In given data, we have depth, breadth, thickness, mx, my, sy, and two materials are given, which is aluminum and steel. And depth is equal to 18 centimeter. Here depth is given in centimeter, so we have to convert it into millimeter. That is 180 mm. And breadth is equal to 6.5 centimeter. Also, we have to convert it into millimeter. That is 65 mm. Thickness is equal to 4 mm, and mx is equal to 5 kilonewton meter. Here data is given in kilonewton meter, so we have to convert it into Newton millimeter. Uh, so that is 5 into 10 raised to 6 Newton millimeter, and My is equal to 5 kilonewton meter. Like that, we have to convert it into Newton millimeter. That is 5 into 10 raised to 6 Newton millimeter, and Sy is equal to 27 kilonewton, that is 2700 Newton, and A1 is equal to E is equal to 70 gigapascal, and G is equal to 26 gigapascal, and still is E is equal to 210 gigapascal, and G is equal to 80 gigapascal. So here is the section properties, that is areas. Area of wave is equal to 720 mm square, and area of top flange is equal to 260 mm square, and area of bottom flange is equal to 260 mm square, and overlap at two corners is equal to 16 mm square, that is subtract to area, and total area is equal to summation of all this, and we will get 1208 mm square. Now we are calculating centroids, that is xw yw is equal to t by 2 d by 2, that is 2 and 90. Now centroids of xt and yt is equal to b by 2 d minus t by 2 is equal to 32.5 and 178, and centroids of xb and yb is equal to b by 2 t by 2 is equal to 32.5 and 2. Now overlaps x0 y0 t is equal to 2 and 178, and x0 y0 b is equal to 2 and 2. Now we are calculating x bar. Here is the formula for x bar, that is xw aw xw plus at xt plus ab xb minus a0 x0 minus a0 x0 divided by a. So we are putting all this value that we have calculated in past, and here is the final answer for x bar, that is 15.13 mm. Now we are calculating y bar, that is formula for y bar is equal to aw plus atyt plus abyb minus a0y0t minus a0y0b divided by whole divided by a. Now we are putting all the values that we have calculated, and the final answer for y bar is equal to 90 mm. Now we are calculating moments of inertia, and for rectangle IXC is equal to BH cube upon 12, and IYC is equal to HB cube upon 12, and for parallel axis IXS minus IXC plus A into dy square, and IYY minus IYC plus A into dx square, After summation, wave plus fringes minus overlaps, that is Ix is equal to 5.7237 into 10 raised to 6 mm raised to 4, and Iyy is equal to 4.5950 into 10 raised to mm raised to 4. Symmetry about horizontal axis is equal to Ixy is equal to 0. Now combine the bending stress. For combined bending stress, here is the formula. My divided by Iyy is equal to 5 into 10 raised to 6 divided by 4.5950 into 10 raised to 5. That is 10 into 10.8813. And for mx divided by ix is equal to 5 into 10 raised to 6 divided by 5.7237 into 10 raised to 6 is equal to 0.87356, and combined bending stress is sigma z is equal to 10.8813x plus 0.8735 y Newton mm square. Here is the bending stress at outer corners. Here is the point x in mm, y in mm, and sigma, that is Newton divided by mm square. Now we are calculating maximum and minimum bending stress from the given table. That is sigma max in tension is equal to 621.28 Newton Newton divided by mm square at top right corner, and sigma minimum, that is compression, is equal to minus 243.26 Newton divided by mm square at bottom left corner. Now we are calculating the shear flow Sy through shear center. Here is the values of y is equal to plus 90 and ds is equal to ds. Here is the formula for shear flow. Q top S is equal to minus Sy by Ixx Tys. Now we are putting values in that formula. Q top S is equal to minus 2700 uh, divided by 5.7237 into 10 raised to 6 into 4 into 90s. That is Q top S is equal to minus 1.694 S Newton divided by mm. At web junctions, S is equal to B is equal to 65. Uh, that is QB is equal to Q top 65 is equal to minus uh, 11.0.38 Newton divided by mm. Now we are calculating shear flow for web and bottom flange. Y is equal to plus 90 minus S. Q web S is equal to QB minus Sy divided by Ixx into T, and integration 0 to S 90 minus mu is equal to du. Q web S is equal to QB minus Sy divided by Ixx T, 90S minus S square by 2. At mid depth, S is equal to 90. Q wave 90 is equal to minus 11.0.38 minus 27,000 divided by 5.7237 into 10 raised to 6 into 4, 19 to 90 minus 90 square divided by 2. Now Q wave max is equal to minus 186.80 Newton divided by mm. Max occurs in tau max 186.80 divided by 4 is equal to 46.70 Newton mm square. Now we are calculating strain due to bending in aluminum is equal to 70 gigapascal, that is 17,000 Newton divided by mm square, and sigma 80 is equal to sigma divided by E is equal to 621.28 divided by 70,000 is equal to 8.88 into 10 raised to minus 3. In steel is equal to 210 gigapascal, that is 210,000 Newton divided by mm square, that is zeta st is equal to 621.28 divided by 21,000, that is 2.96 into 10 raised to minus 3. Now step 2, max shear strain at tau max is equal to 46.70, and in aluminum, G is equal to 26 gigapascal, that is 26,000, and gamma 80 is equal to tau divided by G is equal to 46.70 divided by 26,000 is equal to 1.80 into 10 raised to minus 3. And now in steel, G is equal to 80 gigapascal, that is 80,000. Gamma st is equal to 46.70 divided by 80,000 is equal to 5.84 into 10 raised to minus 4. Now angle of twist. If Sy passes through shear center, torque T is equal to 0, and twist will be 0. Now here is the graph of shear flow distribution. In this graph, we can see on y-axis, here is the shear flow given, and on x-axis distance along perimeter s, that is in millimeter. So here is the final conclusion, and thank you.